Welcome to Math 389 Advanced Analysis. So this is lecture 11. So today we're going to be talking about mean of means. And then depending on how long that goes, we will do some things because tomorrow is PiDay. What is the holiday that competes with PiDay? Tau Day, right? But that doesn't happen until June, and most of you won't be here, but some of you will be here, and so we can do a Tau Day celebration as well. And then if there's still time, I will do another problem where there is some issues with the interchange, and I will do Zeno's bank. So this was shared with me by one of my students in probability who got this from Keith McPartland from philosophy, and I have twisted the problem a little bit to make it a bit more problematic. I didn't think it was bad enough as is. So I will turn it over now to Ami and Nathan, who will talk to us about how many means can we have and various questions like that. So whatever you want to do, you can also draw on slides.
Okay.
Like you need blank slides.
How do I move the slides?
So
swipe them?
Unfortunately, I've never been able to move the slides by just swiping. So I always have to do is I move left like this, move down, and then move back like that.
Okay, cool.
Okay. And then there's chairs if you want to sit down. If I misbehave, you can censor me.
Okay, so we decided to explore the question of means and what that means in general. Pun very much intended. Wait.
Expect nothing else.
Yes. Yes, we're gonna. You should probably tap the actual slide.
So now just slide things back to the left.
Okay. That's fine. Okay. We're going to be talking about definitions and then the growth rate of a particular family of means that we want to explore, then extending the definition, that definition of the mean beyond positive real numbers, and then something we'd call recursive means. Okay, I'm just not going to go back. So, one of the definitions called quasi-arithmetic mean, also called Kolmogorov mean or generalized F mean, proposed building this definition that satisfies, I think, a list of 5 or so axioms, obviously proposed by Kolmogorov. And it's defined as a sum of some transformations of your variable divided by the number of your variables, and then it's fed into the inverse of that function.
Small table, little n is the same as the big N.
Yes, you're right. You're right. Yes.
And can you give me an example of a function that you could use?
For example, reciprocals. I think if you do that, like 1 over x, I think that's harmonic mean.
Okay. But there's another simple example that you should all be thinking of.
Arithmetic mean.
Well, how would you get the arithmetic mean? What would you choose for f?
Oh, just that, just x.
Okay, so if you choose f of x to be x, you get the arithmetic mean. You get the geometric mean. So if you chose f to be like log, then all of a sudden you have the sum of the logs.
Yeah.
That's the log of the product. You bring the 1 over n, and that's the exponent. Then you exponentiate, you get the product of the 1 over n power.
Yeah.
So if you take f of x to be x, it's the arithmetic mean. If you take f of x to be log of x, it's the geometric mean. So this at least encapsulates some of the things we've seen.
Yeah. And I think any kind of power of x also works for this definition. We want to talk about this family of means, which we would define as, well, we did it in class, taking the sum of all combination of k numbers out of n numbers, divided by n choose k, because that's the number of combinations that you can have, and taking the kth root of that. And we could see that for n numbers, you could have n such means.
Yeah, and so
just make sure you're close to the iPad when you're speaking. So
okay, yeah. And so we can extend this definition of a mean by starting to nest the means. So this removes the notion of symmetry we normally hold for a mean, but we keep that each variable can only appear once, so you can't just have an example would be the next slide. So here are some examples of nested means for 4 different variables. So we have like the typical arithmetic and geometric means, and then we can have like a triple mean of 2 of the variables and then the arithmetic mean of the other 2. We could have the same thing of like a geometric mean of the geometric mean of like 3 numbers and some other number and so on. And this obviously has many more means than just the typical 4. And so this is a formula we derive for computing the number of nested means. It's a bit nasty, but it's where Cn is given n numbers, how many nested means can you get? So it's the sum over, like, you divide your, so you find partitions of like n elements, and then for each partition, there are like n normal means, or like n types of means we can have for that. We divide out by q, which is basically like, if I have a partition of 2 elements, of 2 sets of 2 elements, those would be the same, like order doesn't matter in terms of that. And then we're dealing some stuff with like counting and combinatorics. And
So you say that this is with partitions greater than 1?
Yes.
Yeah.
Yes.
If there was only 1 partition, would this be then one of the original means?
It would be just the number itself, right? If you have, so for example, let's say you have 7 arguments. You can represent them as 1, 1, 1, 1, 1, 1, and then it's going to be one of the usual means.
Right.
If you do it as a single 7, that's also kind of like doing 1, 1, 1, 1. So that I think that's double counting. So that's why we exclude that.
yeah.
Okay, I was just wondering if there's a related quantity, if you want to look at all the means that you could get, is you would have to add n to make up for when you only have 1 partition. Then, does this formula capture the arithmetic mean and the geometric?
Yes.
Yeah,
Yes.
yeah, those are captured in like the case where
Decomposition
they're
to
all-
ones.
yeah,
Yes.
completely
So this is to avoid the double count.
Yes.
Okay,
Yeah.
thank you.
Disclaimer: this formula is actually definitely not the simplest form, because the sequence that is produced by this formula is in OEIS, and there are much more elegant formulas to there are much more elegant ways to get to this same result.
Oh, yeah.
But let's see at the actual growth rate of that. Let's look at the growth rate. So this is the log scale, so you can see it's kind of bad. And we have the first 12 values of the formula. I think the easiest lower bound that we can explain right now is n factorial 2 to the n factorial times 2 to the power of n. I think, imagine this. So for example, you have 8 elements. One of the partitions of 8 is 7 plus 1. 7 is captured by the number of means of 7. So let's go with C7. And 1 is another. So in the end of the day, you have 2 arguments. For 2 arguments, you can have 2 means, AM and GM. And n factorial comes from where?
Do you want to read
Permutations, yeah.
the arguments?
That's probably right.
Yeah.
Yeah, I think so.
So you basically you get a recurrence relation for the lower bound.
Yeah.
Yes.
Let's call it L sub n plus 1.
Yes.
Is equal to L sub n times 2 or something like that.
Oh, right. Yes.
So you can write things on slides if you want.
Yeah. Let's do that. Let's go with CI plus 1 is at least I plus 1, I think, times 2 times CI. And I think that's 2 to the n n factorial.
Well,
Yeah.
the I plus 1 c to the I is going to give you the
Yeah.
I factorial,
Yeah.
and then the 2's will just give you the
Yeah.
positive.
But it's much, much higher than that, because 8 has much more partitions than 7 plus 1, and that's even more true for bigger numbers. Okay. I think this definition can be extended to complex numbers, and I think it's going to be even nicer there, because I think it only works nicely with positive reals
Yeah.
because of the roots. So you're not guaranteed to have a root in reals. But complex numbers are algebraically closed, which is good for us, good in general. I like this fact. The only issue is how do you take roots? Because if you don't modify the definition at all, it's unclear if it's a function at all. Because if you take the nth root of a complex number, there are n distinct roots, and so there are two. Okay, actually, not there are more than two definitions possible, but which is settled for taking only principal roots or taking all roots and graphing them. This is what happens if you take the principal roots. I think. So orange dots are actually those labels are swapped. Yeah. Orange dots are original numbers and blue dots are their means. And there are 4 numbers here.
So now when you look at nested means, you could have different roots. And so do you now allow yourself to have different, you don't have to use the principal root every time, but use the principal root here and then something else in the next one?
Well, this graph uses only principal roots,
Okay.
but this one, if you use anything you want, like any of the n possible roots for the nth root, yeah. So you could see that, well, we experiment with a lot of numbers. The resulting graph for non-principal roots approach is usually like somewhat symmetric. We're thinking maybe there must be some measure of a data set being symmetric around the origin. I want to see what the measure is like for different initial conditions. And also we think it can, well, trivially it can be extended to functions of on R+. Actually, as long as the codomain is R+, the domain could be anything, I think. So these are 3 functions. Both of them are red, but I think it's obvious which one is which. The parabola, the trig function, and the log. And the gray ones are all of their nested means.
So what is the x-axis?
The x-axis is x, and the y-axis is f of x. And the f of x, we have 3 f of x's here.
And then what are the plots?
So the red lines are just the functions themselves.
Okay.
The gray lines are nested means of those functions when you take the nested means point by point. And those are also functions, I think. They seem continuous. They seem good. And the black and the blue dashed line and the blue line are just something I thought might be interesting, but I don't know. The dashed line is the AM of all nested means, and the blue line is the AM of functions, not taking into account the nested means. They're kind of similar, but not exactly overlapping.
So then continuing on just exploring means, you can, you can think about what happens if you continually apply a certain like family of means. So in this case, we're taking 24 and 6 and then continually recomputing the arithmetic and geometric mean, and then just iterating this process again and again. So this process, you eventually converge into a single number where the arithmetic mean and geometric mean like agree, and that's the arithmetic geometric mean. This was studied by Gauss, and it does have a closed form. It is a bit nasty, but
It's okay.
yeah. So that's a nice, easy mean formula, which you can use. And so this only works for 2 variables. And so that raises the question of if you could extend this to n is greater than 2. So having more than, just 2 numbers.
So before you extend it, if you go back a slide.
Yes.
Is it easy to show that it converges to something, without determining what the value is, but just that the process converges?
AM and GM, yes. I think we even did this in real analysis class with one of the sets last fall.
I believe it.
Yeah, so it's arithmetic mean, as long as you're taking the mean with something lower than it, it is continuously decreasing, and it's always bounded by the lower of the two terms. Yeah.
Right, so when you take the arithmetic mean is gonna be smaller than the larger.
Yeah.
And the geometric mean is gonna be smaller than the larger.
Yeah.
So you have something that's monotonically decreasing.
Exactly, and bounded.
And bounded, and so then you can appeal to some results from real analysis that
Yeah.
must converge.
Although I think this argument can be extended to 3, but it's not as easy because you have.
Step in the middle.
Yeah, but we could talk about it later maybe. Well, spoiler, we don't have a closed form for n more than 2. Sorry.
Yeah, and so this would be a definition of a recursive non-nested means. We'll talk about the recursive nested means later, but it is not as fun. So given like some array of numbers, what you do is you take all of the means we previously described, or the family we're studying, and you apply those, creating another vector of length n, and then you just keep reapplying the means again and again. And this, we're hoping that this vector either converges to some stable vector where like all the numbers are fixed, or ideally that all the numbers are the same.
Yeah, although we believe that, well, all the experiments show that they converge to the same number, but I think it can be also theoretically, maybe quickly shown that it cannot be a stable vector of distinct numbers, because if those numbers are distinct, then AM is not going to be equal to the first number, to the biggest number of them. So if they, I think if they converge, which we think they do, they converge to a single number.
Right.
Okay, yeah, that's why we think it converges. The same can be done for complex means, recursive non-nested complex means. So for the array of n elements, you continually have arrays of n elements. And this is the plot that you have. Well, I think the colors are somewhat unfortunate, but these are red, so these are earlier iterations, and this is dark blue, meaning that most of the action is happening here. This, I think, under the hood, this has about 1,000 iterations, but they're getting super close to each other here. And again, all the experimental values converge to a vector of 4 identical values. And the last thing that's super interesting, I think, but we don't have a way to compute that. Do non-nested means converge to anything? Let's say you start with 3 means. 3 numbers, original numbers. By our formula, they have 15 non-nested means. By our formula, they have 10 to the 19th nested means. I don't know how many means the 10 to 19 means have. So that's kind of a lot. We cannot do it even for the first. N equals 2 doesn't matter because 2 always has 2, so it's going to be always AMGM. So it doesn't matter. Gauss proved that. But we cannot test it even for the first number after 2. So that's bad. And we think, well, if we're to solve this, there must be either some analytical methods or some ways to, I don't know what I'm talking about, but some ways to choose only some of the means and show somehow that it's equivalent to taking all of the means, if that's even possible. That's the only like computationally tractable way.
Well, what you could do is you could say, I'm going to compute the new arithmetic mean, the new geometric mean, and the new triple mean.
Yeah.
Just keep iterating those.
Well, yes.
Or just specify, I have 3 numbers, I'm going to choose 3 means from my set of all possibilities, my 15 possibilities.
Yeah.
And I'm always going to use those 3 means.
Yeah. Is it going to be the same? We don't know.
So that would be an interesting question. So you have 15 means.
Yeah.
You have how many ways to choose 3 numbers, 3 means from the 15? Is it 15 cubed? Because you could do the same thing multiple times. You have to worry about ordering. I don't know.
I think the true mean, like the mean of 15 numbers, is going to be probably slightly lower than the 3 means, because means are probably a little bit closer towards the GM.
No, but just saying you have 15 possible
Yeah.
choices for means.
Yeah.
So if I have 3 numbers, I need to choose 3 means from the 15.
Yeah.
So they give me another set of 3 numbers.
Yeah.
How many ways can I choose that? Is that just 15 cubed? I have,
Well, 15 times 30, 14 times 30. Well,
because I could use the same thing multiple times.
well, that's,
I guess.
I don't know. That's, yeah.
So,
yeah.
so
Yeah.
If you elaborate, but it's,
you say that that's boring or not fair to use the same thing
Yeah.
twice, then you can say it's 15 times 14 times
Yeah.
14.
Yeah.
And so I need to choose 3 distinct means, so it's 15 choose 3.
Yeah.
And then the question becomes, no matter what choice of 3 of the 15 means you take, will it eventually converge to something? And how does what it converge to depend on the choice?
Yes.
So for instance, if you always choose the arithmetic mean, it should immediately converge to the arithmetic mean.
Yeah.
If you always choose the geometric
Yeah.
mean, it should immediately converge to the geometric mean.
Yeah. Same with
So
that.
the answer should, so by looking at extreme cases, we can see that the answer depends on
On the choice of
choice.
means. Yes.
Yeah.
There is one more question that we didn't include on the slides that I also think is interesting. For example, if you reverse the problem, if you have an array of n unknown numbers, let's say real numbers, real positive numbers, and you can choose, for example, let's say you have like, I don't know, like boxes of all nested means. You can look at only, like you can look at the inside of only k of them. Which ones should you pick to have a better understanding of what the original numbers are?
And that's going to depend on what you mean by
Yeah.
understand.
Yeah. Well, what's better is can be like maybe volume or the shape of the thing that you get out of combining k equations. If it's bounded, then it's probably better. If you know the boundaries for all of your n numbers, then you can probably say, okay, it's probably volume of the shape, n dimensional volume of this, not n minus k dimensional volume of the shape, right?
Okay. Thank you.
Yeah.
Any questions from the class? So I guess one question is how much of this is known in terms of, you said that the formula for counting the number of nested means is known.
Yes, but
Yes.
I think it was derived from something else,
Yeah.
because I think, well, if you go back here, you could see that this is somewhat like a tree notation, right?
Right,
You can see it. And I think the original thing was the original problem was posed in terms of graphs of trees, probably. How many ways can you make a tree that
Yes.
doesn't have one child, that has like maybe no leaves
Yeah.
or something like that?
And then you consider that, for the third line, you have TM, AB, and the AM of CD. If I commute the orders of A, B, C, D, is that now considered something new?
No.
No.
Okay.
So in that way, it's very similar to a graph.
So that way it's very similar to a graph. It's you're basically trying to come up with the number of legal ways to combine these operations.
Yeah.
Yes.
The Catalan numbers is basically the number of ways to legally combine binary operations. It's basically putting in parentheses how many legal ways can you throw in parentheses so that you never see more right parentheses as you walk down the left parentheses.
Okay.
So it's a valid partition.
Yeah.
Process. And now this problem is harder because you don't have to do binary combines.
Yeah.
You can do ternary, quaternary, and so on.
Yeah.
And also another, I guess what you said for partitions, I just realized another, I think probably easy lower bound on that is the rate of growth of the partition generating function. Because it's definitely going to be more than that.
Right.
Yes.
Yeah.
So.
It's great when you see things going this rapidly. So email me and we'll try to figure out if there's more that you want to do. This can be, again, I think writing up an article on the mean of means and coming up with these statistics, I think that would be a really nice Math3 article, because too many times when people are starting out, they're told what to study. Why do we study this? Well, as you get older, you start to realize certain things are better than others. Who here has taken a stats class? Right. Who here has done linear regression or the method of least squares? How do we measure errors? Squares. Why do we use squares of errors? Because now, if you have one bad data point, it has a magnified impact. If you use absolute values, differentiable. The absolute value function is not differentiable. The square function is. If we use squares for errors, all of a sudden calculus and linear algebra are available, and we can write down a closed form solution for the best fit parameters. The way I like to phrase it is, if I'm hired as a consultant, I use the method of least squares and linear regression. If I'm hiring somebody, I want them to use absolute values. And for that, then you have to resort to numerics. We don't have a closed form expression in terms of the inputs. This is a big theme in mathematics. When do you have a closed form expression? Closed form expressions are wonderful. If I then vary a parameter, I can then see what impact does that have without having to do expensive simulations. And so here, this would be a great math outreach article where the idea is, how do we come up with a statistic to study? Well, we want a statistic like the mean to have a couple of properties. What constraints do those impose on us? What are acceptable means? And then which constraints are you willing to drop? So years ago, I was doing a consulting project for a movie theater. And one of the constraints they had was a movie had to start every 20 minutes, so that if somebody just showed up, they would never have to wait more than 20 minutes. This was, more than 20 years ago. Nowadays, how many of you just show up to a movie theater, assuming you even go to a movie theater anymore? What do you do before you go to a movie theater?
Right. Yeah, check the schedule.
Check the schedule, buy the tickets online and whatnot. So it's not as big of a deal in terms of showing up. But, in the old days, it was more of a big deal. And it was a hard constraint. We then told him, if you occasionally have gaps of maybe 25 or 30 minutes, we think we can increase profits by this much. At which point it was, yeah, we could have a few longer gaps. And it's just, what is the problem you're trying to solve? Do we really need symmetry? Well, if we do symmetry, then all exams are the same. And so you can't have a final counting more. And if you did poorly on the first midterm, well, I'm sorry, you screwed yourself for the entire semester, right? So some of these constraints, which might initially seem reasonable, might turn out to be quite absurd. And so then you can ask, what's the minimal set of constraints I need for something to be interesting? All right. Because we are closing in on PiDay, I figured that I would use some of the remaining time today to at least do something in honor of PiDay. The only rule is it has to involve something illegal with an interchange of operations. And so I will do one of my favorite formulas. Anybody know the formula involving G and L? Gregory, you're studying German now, so famous German mathematician, Leibniz. So, what is the derivative of arctangent of x? Does anybody remember?
Like 1 over 1 plus x squared.
Yes. Now, if I give you f of g of x equals x, that implies f prime of g of x times g prime of x equals 1. So g prime of x is 1 over f prime of g of x. You should have hopefully seen this in a calculus class. What this allows you to do is, if you know the derivative of a function, you can get the derivative of its inverse. So if I know the derivative of the exponential, I know the derivative of log. So can you come up with a good function to have hit arctangent? So what would be a good function to apply to arctangent of x? Tangent, right? What is the tangent of arctangent of x? X, right? Just say it out loud. I'm asking for the tangent of the angle whose tangent is x. Oh, okay. So that implies arctangent prime of x is 1 over tangent prime of arctangent of x. Anybody remember what the derivative of tangent is? Secant squared. And again, there is a reason why secant goes with cosine. It has to do with the angle and the coangle. I would much prefer to have cosine and cosecant together and sine and secant together. Not happening. This is the same as cosine squared of arctangent of x. Because since the derivative of tangent prime is secant squared, 1 over secant squared is cosine squared. Okay, so we know the derivative of arctangent is cosine squared of arctangent of x. But cosine squared of arctangent of x is kind of tough to parse. So let's draw a triangle. So I'm going to draw an angle whose tangent is x. What would you like to make the vertical line?
X.
X. And the horizontal line? 1. And the hypotenuse is the square root of 1 plus x squared. So now from this we get that the cosine of arctangent of x is 1 over the square root of 1 plus x squared. So cosine squared of arctangent of x is 1 over 1 plus x squared, and that's arctangent prime of x. So here's the trig proof that the derivative of arctangent, okay. If I'm nice to you, I will give you integrate a constant. If I'm slightly cruel, but still pretty nice, I would ask you to integrate f prime. So what is the integral from 0 to 1 of arctangent prime of x dx? So what function has derivative arctangent prime? So I want a function whose derivative is arctangent prime of x. Arctangent, right? Every now and then I'm nice, right? What function has derivative arctangent prime? Arctangent. Evaluate this at 0 and 1. What's the arctangent of 1? What angle has a tangent of 1? Pi over 4. And we do things in radians. We've already seen numerous times that whenever we do differential trig, it's got to be in radians. What angle has a tangent of 0?
Sine of 0, which is pi over 2.
Nope. Sine of pi over 2 is 1.
Oh,
0. So it's just pi over 4. So this integral is pi over 4. Well, this integral is the same as the integral. We know that the arctangent is 1 over 1 plus x squared is the derivative of arctangent. Does 1 over 1 plus x squared look like anything you've seen before?
Yeah.
What does it look like? Geometric series. What does r equal? If it's a geometric series, you have to tell me the ratio. Nope, you're close. So I want 1 over 1 plus x squared to equal 1 over what?
1 minus r.
1 minus r. So what does r equal? Negative x squared. Right? So this is the same as the integral from 0 to 1. The sum n goes from 0 to infinity of negative x squared to the n dx. Right? What's the integral of a sum? Some of the integrals. You got to do better. You can't keep your hands crossed. Okay, you got to be moving the hands of some of the integrals. With this look of disgust on your face, like, how are you even asking me this? Of course, the integral of the sum is the sum of the integrals. How could it be anything else? So it's the sum n goes from 0 to infinity. I can pull out the negative 1 to the n. I have the integral from 0 to 1 of x to the 2n dx. All right. What's the integral of x to the 2n? So x to the 2n plus 1 over 2n plus 1. I evaluate that at 0 and 1. Oh, that's nice. I just get... So this is just the sum, n goes from 0 to infinity, of negative 1 to the n over 2n plus 1. And so I'll switch to red. So pi is equal to 4 times, when n equals 0, we get 1 minus a third plus a fifth minus a seventh. And there's the formula for pi. The formula converges slowly. But if I stop here, upper or lower bound? Lower. And if I stop here, upper. So what's nice about this formula is where I truncate it, I get an absolute upper bound, absolute lower bound. I can get a range where pi lives very easily. I can check later, but that seemed like 2 minutes once I had the derivative arctangent. That was pretty fast. Does anything bother you?
Swapping the orders.
So what do we need to be able to swap the order? So if you take the absolute value of x squared, what's going to happen? So then you would basically get this without the minus signs. You would get essentially half the harmonic series, which blows up. So we can't use that. However, when you look at this, I mean, come on, it's alternating. It shouldn't be too bad. Does anybody know how we could fix this? So sadly, the integral of the sum of the absolute values is infinity. So danger. There are ways to fix it. Any thoughts? So we need to modify the integral from 0 to 1, the sum, and goes from 0 to infinity of negative x squared to the n dx. What should I replace the upper bound with? Instead of integrating all the way up to 1, what could I integrate up to? I'm sorry? Okay, and how do you want a to be related to 1? Going towards 1. So I could do a, or I could do maybe 1 minus epsilon, and then take the limit as epsilon goes to 0. Now, what can you tell me about the integral of the sum of the absolute values? So now the integral from 0 to 1 minus epsilon, the sum, and it goes from 0 to infinity of the absolute value of negative x squared to the n dx is finite. So for each epsilon, this is finite. And so now we get pi is equal to the limit as epsilon goes to 0 of 4 times. So it's going to be 1 minus epsilon minus 1 minus epsilon cubed over 3 plus 1 minus epsilon to the 5th over 5 minus dot dot dot. Now can I take the limit as epsilon goes to 0? Yes, this is going to be fine. I have an alternating sum. You could also try to play some games by grouping things in groups of 2. But really, the difficulty is things blow up when x equals 1. And so if we just stop just shy of that, we're okay. The other question, of course, is rather than integrating from 0 to 1, is there another value we could integrate up to where we know things? Well, we integrate from 0 to 0, yes, we know it, but it's not going to help. So we want to integrate from 0 to some nice theta of arc tangent prime of x dx. That's going to be, let's not call it theta. Theta would be bad. Let's call it a. And so this would then be arc tangent of a, because we know the arc tangent of 0, 0. So can you think of any a where we can calculate the arc tangent nicely in terms of pi? Okay, so if I give you theta equals pi over 6, what's the tangent of theta? So pi over 6, pi over 6 is the smaller angle, right? So it's pi over 6, pi over 3, and 90. Pi over 6 is also known as what angle? Oh, wait a minute, maybe I did this wrong. Oh, no. Sorry, this is 30. So that's 30 degrees, and this is 60 degrees.
No, that's not square root. It's square root of 3 is pi over
So if you think about what's going on, if you repeat it down here, this is 1, this is 1, this is 1, this is 1, this is root 3 over 2, I think. We've normalized things. And so each of these over here would be 1/2. Right? So what's the tangent of theta? 1 over square root of 3. Or root 3 over 3. So if we take the other thing is we could have done theta equals pi over 3, and then the tangent of that theta would be root 3. So which do we want? 1 over root 3 or root 3 for our upper value?
Well, should it be less than 1?
It should be less than 1, right? So since we want it to be less than 1, that's a strong argument to try pi over 6, right? So let's take theta equals pi over 6 as the arctangent of root 3 over 3 equals, okay, pi over 6. Okay, and so if we set things up right. So taking a, okay, and a equals root 3 over 3 is less than 1. So if we do that, we stay inside the region where everything is well behaved. And so now we would get the integral from 0 to root 3 over 3 of 1 over 1 plus x squared dx is going to be arctangent of a. So that's arctangent of is going to be pi over 6. Therefore, pi is equal to 6 times, and now we would just do the same argument as before, and then we would get 1 minus root 3 over 3 over 3 plus root 3 over 3. Oh, sorry, this one should be cubed. This one should be to the 5th over 5 minus dot dot dot. I don't know if I made a mistake on the previous one. No, I did not. Okay. And so that would be a formula for pi. Is that a better formula? Yes or no?
Are going to use.
Why? All right, so let's see if it's really more annoying. So the root 3 over 3 cubed, well, I'm going to get an extra root 3. So for all of these, wait, should the first one, should that one be a root 3 over 3 actually? This should be a root 3 over 3, right? So everything is actually going to have a root 3. So I can pull out a root 3. So it's going to be 6 square roots of 3. And then let's look at what we have. We then have 1/3 minus, now we have a root 3 cubed, but we're going to remove one of them. So it's a root 3 squared. So it's 3 to the 1st. We have a 3 cubed, so that's a 3 squared. So I think it's minus 1 over 3 cubed. The next one, we have a 3 to the 5th. We have a root 3 to the 4th, which is a 3 squared, over 3 to the 5th is a 3 cubed. So it would be 5 times 3 cubed, I think. And then we should not write this as 3 cubed. We should write this as 3 times 3 squared. And we should write this as 1 times 3 to the 1st. And then the next term, we're going to have a 3 to the 7th. We have a root 3 to the 6th, which becomes a 3 cubed. So that's a 1 over 3 to the 4th. So it's going to be 7 times 3 to the 4th with a 1 versus pi equals 4 times 1 minus 1/3 plus 1/5 minus 1/7. So which formula do you prefer? There's something, I think, intrinsically beautiful about the alternating sums of the reciprocals of the odd numbers. I can say that nicely. I can't say in English nicely the other sum. But what does the other sum have to its credit?
Converges even if all the signs are pluses.
Right, but I mean, but all the signs aren't pluses.
Yeah, but even that, I think, even that it converges. Right?
Yes, but for the second one, if all the signs were pluses, I'd be in trouble, but all the signs aren't pluses. What does the first expansion for using 6√3 have over the second? Why is it a better expansion? What property does it have? So in the real world, it's not enough to converge. I want to know what. What converge to, and what else do I want to know? How fast? Yeah, look at how much faster the top converges to the bottom.
Think how much fun you could have with going through all of the alternating sums.
Absolutely. And in fact, what you can do is you can add the alternating sums in groups of 2, and it will converge a little bit better like that. But the top one has much better convergence because now you've got geometric decay coming in as well. So the question is, can you do better?
Yeah, I just said pi equals pi, and then it's done.
Well, but the problem is, if you want to do pi, we have to make sure that we only integrate to something less than 1. So we did 30 degrees. Can we do something better than 30 degrees?
Does better mean smaller?
Yes. The smaller it is, the faster it will converge. And again, right now, I'm assuming I know square root of 3 perfectly. So you always want to look at trade-offs. So this converges faster. But here, you don't need to know the square root of 3. Right. So for the top one, it converges much faster, but I need to know the square root of 3. But if I wanted to approximate pi squared, then that would be fine, because I'd then have 36 times 3 is 48 times whatever that quantity is squared. Yeah. So if I want to actually approximate pi squared, this gives a nice approximation for pi squared. So whenever you have a disadvantage, change the question and make it an advantage. Oh, no. It's not a disadvantage that it has a square root of 3. It's an advantage that now if I want to calculate pi squared, everything is going to be nice. In computer science, it's called saying it is a feature, not a bug.
Exactly.
And so a feature of this is it's beautifully positioned to calculate pi squared very rapidly. So how many of you have seen the Gregory-Leibniz formula? So this is a wonderful result. So if you haven't seen it, again, in your math majors, something's wrong. You should have seen this at some point in your career. To do it carefully, we have to be a little bit careful about interchanging orders. It's simplest to do it when you integrate from 0 to 1, but then you have to worry about what's going on. So we can take limits as epsilon goes to 0 and play all those games and use the Fubini theorem. If we do it to √3/3, it's much nicer. So can you think of another angle where we know the arctangent, the tangent very nicely, and it's going to be even less than √3/3? Is there an angle you can compute?
No, 0.
You know 0, but 0 is not going to help us. So we know 60, we know 45, we know 30. Anything else? So sad how little you know. 15, yes, excellent. We know 15. Well, 15 degrees is pi over 12. How do we calculate that? You derive it. So do you remember how you would derive the double angle formula? So let's try to do, so if we want to do the sine of x plus x, that's sine x cosine x plus cosine x sine x. The sine of x halves plus x halves is the sine of x is the sine of x halves cosine x halves. Well, we just double it. What about the cosine of x halves plus x halves? That's the cosine of x. That's going to be cosine x halves cosine x halves minus sine of x halves sine of x halves, yes? That's cosine squared of x halves. Sine squared is 1 minus cosine squared, so this is 2 cosine squared x halves minus 1. So we get 2 cosine squared x halves minus 1 is cosine of x, and we get 2 sine of x halves cosine of x halves is the sine of x. So the cosine of x halves is cosine x plus 1 over 2. Yes? And square root, of course. And then the sine of x halves is going to be 1/2 the sine of x over the cosine of x halves. And we know what cosine of x halves is from above. So if I know the sine and the cosine, I actually know the sine and the cosine of half the angle. So I can figure out pi12s. That's going to be a smaller number, so it's going to converge faster. So let's calculate just the sine or the cosine of 15 degrees of pi12s. So the cosine of pi12s would be the square root of the cosine of pi6 plus 1 over 2. What's the cosine of pi6? So if we go back to our triangle, square root of 3 over 2. So we get root 3 over 2 plus 1 over 2. All right, so this becomes root 3 plus 2 over 4 square root. Well, the 4 down below, when I take the square root of that, I just get 2. And so now, is the number reasonable? Good, it's smaller than 1, right? It's less than 1, so it's at least reasonable. Yeah. You know, if I replace the 3 with a 4, I would get the square root of 4 plus 2. Good. So it's at least 1, so it's a reasonable number for a cosine. And the hope is that this will actually give you now a smaller, and it will give you a better formula. But now you need to know the square root of 3 plus 2. Right, but if you want to do something exactly, right, that's the problem. And we now have to start raising this to powers. And so the question is, does this become nice? Well, I need to see what the tangent is. Maybe there's some cancellation. So as an exercise, find the tangent of pi over 12. How should we find the tangent of pi over 12? Yeah, Wolfram alpha. I mean, you can see I'm playing on my phone right now, right? Yeah. The first thing you do is you go to Wolfram alpha, go to the little box, and I'll write, you know, the tangent, and I want pi divided by 12. And so when I plug that in, it says it is equal to 2 minus the square root of 3. And it is approximately 0.2679. That's, and root 3 over 3 was more than that. So this is actually a better number. 2 minus root 3 is not terrible.
As bad as root 30.
I'm sorry?
It's as bad as root 30.
No, it's actually much worse. Because when you when you square it, and so again, when I take 2 minus root 3 to the n, that is of the form a sub n plus b sub n root 3. And you can figure out what those integers are. So you can get a formula for pi is equal to some integer plus some integer times root 3. So it all comes down to what are you willing to use? What do you know? And then are there other integrals you can do in closed form? So I know at least 2 people here, including people in Zoom land, have taken complex with me. And so we can evaluate certain integrals by using contour integration techniques. So maybe there are some other things you can do that would get you like 1 over 1 plus x to the 4th. And that might have your slightly better convergence. But it's not going to be terrific. And so it's a real quest to find efficient formulas to compute pi. There are some beautiful formulas that allow you to jump to any specific digit. It's a base 16 expansion. Well, yeah, you take what you can get, but you can just jump to the nth digit base 16 without pre-computing all the other digits. That's wonderful. And different formulas converge at different speeds. The Gregory-Leibniz formula, I think it's beautiful. The alternating sum of the reciprocals of the odds, it flows off the tongue. Its convergence is not great. And you can ask, how many terms do I need to get, 5 digits? It's not going to be good. Because, it's going to look like the tail is like 1 over n squared. So when you keep summing that, it becomes a 1 over n. So you're going to need, maybe 10 terms to get 1 digit, 100 terms to get 2 digits. It's bad. The next formula that we came up with was actually much better, where we got these powers of 3. We did have the square root of 3. And so if we want to calculate pi squared, that's not bad. So what's interesting about this is if I was directly going for a formula for pi squared, I don't know if I would have come up with this. But looking for a formula for pi, this led to a very nice formula for pi squared. Do you know how the statistician always gets a bullseye? This is an old joke. You shoot first, and then you draw the bullseye. And by doing it, this is a class on the interchange of order of operations, right? So, what do? I shoot, and it lands here. And so I'm going to draw my bullseye right here, and that's perfectly in the center. Then I'm going to shoot again and over here. And now I'm going to have, actually, this was a really impressive shot because it was a small bullseye. It was a small dartboard. I got it. So you change the target. So you don't say, I was trying to compute a formula for pi and failed. I said, I was going for a formula for pi squared and succeeded. And you just, this is how, I know this is being recorded, so this is probably going to bite me, but you can be honest and say, look, we were searching for a formula for pi. We found a formula for pi that converged very rapidly, but it requires us to know the square root of 3. And it all comes down to what tools do you allow yourself to use? Do you remember geometry?
It's a very broad question.
This should be a pretty easy question. So in the straight edge and compass constructions, what can you use? No, it's actually a compass and straight. No, yes, it's a straight edge and compass. My son would do that to me. Yes, right? And so why just those tools? The Greeks like to challenge. You can't mark lengths and record their value. And so the question is, what can you do with a straight edge and compass? And one of my favorite things that you can do is you can construct square roots. And there's lots of ways to construct a square root. What I can do is, let's say you give me a number x. I can form a circle with diameter 1 plus x. And so over here, I'm going to draw something, this is going to be x plus 1 over 2. And I can draw, so actually, if I'm going to do this, I might as well draw my line this way. Oops. So let's call this y. Does anybody know the relationships between y, x, and 1? So anybody remember their geometry? All right, let's start drawing lines. So let's just give everything names. Let's call this A, let's call this B. So we know 1 squared plus y squared equals a squared, right? And we know x squared plus y squared equals b squared. Do we know anything else? Any other right triangles?
Yeah.
Yes.
B squared plus a squared is 1.
And which side do you want the b squared plus a squared on? The left or the right? Yeah. A squared plus b squared is 1 plus x quantity squared. So if I add these two, these are the same, right? Therefore, 1 squared plus x squared plus 2y squared is 1 plus x squared. So 1 squared plus x squared plus 2y squared is 1 squared plus x squared plus 2x, right? And now, just canceling, we get y squared equals x, or y is the square root of x. So here is a way using just straight and compass to construct the square root of x. I just create a circle. I can always create a circle. You always assume you have a segment of length 1. That's one of your starting points. I can then extend the segment of x to be of length 1. Can I find the midpoint of that? Sure. What you would do is, if you have a segment, what you can do is you can draw a circle of that radius from both endpoints that gives you 2 points of intersection. You come down like that. And so now I have this point of intersection. I have this point over here, which is the distance of x. I can construct the perpendicular bisector to the line over here. These are all constructible. So I can construct the square root of x. So is the square root of 3 a bad number? It's not an integer, but it's not horrible. And so in all of these problems, you always want to get a sense of how bad is a result. Does anybody know the standard formula people use for pi squared?
Oh, I don't know if it's standard, but the sum of 1 over squared
Yes.
times 6.
Pi squared over 6 is the sum of 1 over n squared, and it goes from 1 to infinity. And has anybody here not seen the Riemann zeta function? Has everybody seen the Riemann zeta function? Zeta of s is defined as the sum, and it goes from 1 to infinity, 1 over n to the s, and it turns out it's the product over primes of 1 minus 1 over p to the s inverse. Is there anybody who, if you haven't seen it, that's fine. It's not a prerequisite for this course. Okay, so this converges if the real part of S is greater than 1. Now, here's two nice results, and we'll end the class with this. If you take the limit as S goes to 1 from above of zeta of S, this goes to 1 plus 1/2 plus 1/3 plus ... equals infinity, therefore infinitely many primes. Right? Because if there are only finitely many primes, then the product would be finite. Okay? It's a deep result that when you take S equals 2, you get pi squared over 6. In fact, all the even integers give you pi to powers. The odd numbers are unknown. We have certain results such that at least one of the following 5 numbers gives an irrational value of zeta when you evaluate it there. There's strange results like that. Here is a nice theorem. This is one of my favorite theorems in math. Pi squared irrational implies there exist infinitely many primes. Why? If only finitely many primes, zeta of 2 would be the product over p of 1 minus 1 over p squared inverse would be rational. So if you can prove that pi squared is irrational, you can prove that there are infinitely many primes. Have you seen Euclid's result? That there are infinitely many primes, multiply all the primes and add 1. Has everybody seen this? And this gives you, if you let pi of x be the number of primes less than or equal to x, Euclid gives pi of x is greater than, say, some constant times log x. The truth is pi of x is about x over log x. So Euclid's result is really bad. Your worst case is assume the next prime number is the largest it could be, and that you don't have anything earlier. So you're squaring what you had before. And in that case, there's at least log x primes up to x. So in case anybody ever feels like they can't make it as a mathematician, the following result is due to me, but I improved it with some students. There's something called the irrationality exponent. Irrationality exponent. I use that of pi squared, and I get that pi of x is at least log x with some constant. Worse than Euclid. The proof of the irrationality exponent uses the prime number theorem. So using as input that there's about x over log x primes up to x, I can prove that there's at least log x primes. You will have to work hard to have a worse result than that. Thank you. Did not publish it. I did improve it with students, improved with students. I'm sorry? You get log x. Yes, I can get that trivially because that's less than. So I improved and got a better result unconditionally. And the reason I'm ending with this is I just used the result about the irrationality exponent, and then I went to the paper to look up how did they prove it, and noticed in the proof they use the prime number theorem. You have to be very careful to avoid circular arguments. We saw that with L'Hopital's rule. It's so easy to accidentally assume something. And so especially when you get to basic questions. All right, so this is a good place to stop. Have a good PiDay tomorrow.